So, hello and welcome to the DB Digest. My name is Brody, and this is your monthly digest of insight from design verification leaders. Now, our next guest on the podcast is a guy called Andrew Bond. Andy has spent the last 25 years in verification. He's had 10 years at Nvidia, Cirrus Logic, a low latency trading firm called Jump Trading, and he's now the director of verification at an edge AI processor company called Axelera. We talk about a few different things. We talk about Python as an alternative to SystemVerilog and its benefits and when you should be using it. But we also talk about Andy's new alternative to UVM built in Python, an open source library called AVL. I think it's a super interesting conversation. I'm super glad that Andy decided to announce his library on the podcast, and I really hope you enjoy. So, Andy, welcome to the pod. I appreciate you coming on. I think we should get right into it. Why is Python better than SystemVerilog? What's wrong with SystemVerilog?
Well, first of all, thanks for inviting me along. I suppose I should start with the first thing. There's nothing wrong with SystemVerilog. SystemVerilog has been perfectly good. It was a big step forward 20 years ago when it came through. And I'm going to sort of combine it with UVM and SystemVerilog as the same thing. So as I always say, UVM was a big step forward, and the days of ERM and VRM, when we finally agreed and all did the same thing, was a big step. But there's a couple of issues with it. So the first one being that SystemVerilog isn't really a language. It's only supported by a subset of simulators, generally the big 3 or 4 EDA vendors. And the support for the different language constructs is different between them. Yes, there's an LRM, and you would have thought that would have been fully implemented by everyone, but it's not quite true. But the big thing for me is that UVM and SystemVerilog can be quite time consuming to develop. So particularly UVM, it's very boilerplate code. You have to write a lot of code, particularly around parameterization, and that can be quite slow to develop. There are tools, DVE and other things that can help you generate baseplate code very quickly, but it still takes a bit of time. And the second part is that the compile time. For me, the most important part of a verification tool or methodology is how effective it keeps people and how productive people feel. And when you make a SystemVerilog change or a UVM change, yes, you can have partitioned your code, you can have multiple libraries, you can do recursive and non-change compilation, but it still sometimes takes a minute, 2 minutes, 3 minutes to compile, depending on how big your test bench is. And every minute that your verification engineer is not actually debugging something is a waste of time. And the great thing about Python is it's interpretive, and you can change it and you get a syntax error immediately, and you can change and rerun your code 5 or 6 times in the time it would take to make one SystemVerilog change. I think the last thing to say on this is really that is to take advantage of the community. Python has a massive open source community. They've written a bunch of really useful libraries. So some things that are kind of awkward in SystemVerilog, like reading files, processing text, Python's amazing at that. There's loads of open source libraries. You can use pandas, you can use any kind of YAML interpreter. It's amazing for that. And certain things that are becoming more and more prevalent in verification now, such as debugging encryption or doing data analysis, Python has those libraries already built into them. Whereas SystemVerilog, you have to develop those yourself, or you try to buy them. But there's not that massive library of community-based code.
Yeah. Okay. One other thing, because you did a talk at this conference that we both went to, and you mentioned how a lot of developers, a lot of verification engineers, are using Copilot or ChatGPT or something similar to develop their code base. You made a point about Python and that being better suited for that sort of development environment. Could you just expand on that a little bit?
Yeah, so I think there's what we've got today and there's what might be coming in the future. And I think what we've got today, if you play around with things like ChatGPT or Anthropic or GitHub Copilot, any of the big names, They've obviously scraped and consumed a lot of information from the internet. And the great thing about things like C code, C++, or Python is there is a massive amount of source code available. And so the sort of hints and tips you get from Python or C++ is significantly better, in my opinion, than you get from SystemVerilog. SystemVerilog's because it's a kind of a proprietary simulator-based language. There's not a lot of open source SystemVerilog out there. Certainly not a lot of good code to be trained on. So you will find if you've been playing around with ChatGPT, the amount of support for Verilog and SystemVerilog is much better than it was a year ago or 2 years ago. But every day more Python code gets scraped and learnt from than probably the entire history of SystemVerilog. So the kind of hints and tips are really much better from that front.
Yeah, okay. I mean, that makes total sense to me. When I was doing my research for this, there was one thing um, that seemed like a bit of a concern on the Python side. There seems to be a lot of workarounds in Python that are sort of native to SystemVerilog. So the randomization part and things like that. Is that going to make things less effective, less efficient? Is that going to make things worse generally, for the loss of a better word?
Yeah, so I think there's a couple of ways of thinking about this. So uh, you're right in that SystemVerilog has really opened the doors to constrained random and that kind of development. Now, Python has always had a randomization element to it already. So there was always the random library and the NumPy randomization, which is really good. But you kind of at the moment have to change your way of thinking. You don't have the implicit constraints which are bidirectional and can affect multiple variables at the same time. You kind of have to do it sequentially. However, uh, there are other libraries available. So there is things like Python constraints library and Z3 from Microsoft, which do random constraint solving. Uh, they take a little bit of interpretation, but they can do that. I think I think you've highlighted one good point that this would be a change to people's way of thinking. There's other things uh, like Python effectively being very function based, and if you sit on the shoulders of CocoaTB, there's a few other libraries out there, but I'll talk about CocoaTB. Uh, they've already solved that problem for a lot of people. They've already solved the tasks and functions time-consuming elements, which makes things a lot easier. Uh, in terms of other challenges, there is the problem that simulators do not naturally waveform or do not support Python. They think of it as a plugin or a third party, kind of how they used to with PLIs and VPIs. Uh, but in my opinion on this one's beginning to change. So EDA vendors may start supporting it, but more importantly, I think as people go to larger designs, uh, the style of debug we do is a bit different to what it was 15 years ago. So the idea of waveform debug and in simulator debug is kind of changing. I must admit, for me, if I have to open a waveform, it's really a last resort these days. I would really much rather debug a text file or some kind of constructed logging that makes things searchable and easier to do. Uh, there are ways around this in Python. You can use interfaces, you can drive debug signals, uh, and in many ways they're not significantly worse than the class-based debug you already get with simulators. Uh, I'm not going to knock the vendors, but when you use yeah when you use a sort of a class-based UVM test bench, the way variables, particularly for things like queues and dynamic arrays, are displayed isn't as good as it could be anyway. So those things are quite hard to debug on waveforms anyway. You have a similar problem with Python from that side.
Okay. So again, obviously, I'm not a verification engineer, but these sorts of does any of this make things harder for verification engineers, or does it make it less likely that you're going to verify things successfully and you're not going to have, a failure post silicon? Like, is there any drawbacks here at all?
So I think there's probably two limitations that probably come up quite a bit, which you have to be aware of. I think that if you're constructing a test bench, you understand the limitations of randomization, you understand the limitations of the visibility. There's probably two things that catch people out more commonly than else. The first thing is that Python is two-state, so it doesn't have X's and Z's. So you have to be very careful when you're developing test benches for things that have tri-states or real pads or real models. Uh, and as long as you know that and you take that into account, you can work around this. I'm not one of the religious ones that believe that you should never have any Verilog in your test bench. I think do what makes most sense. If you need to have support code in SystemVerilog, put support code in SystemVerilog. Whatever works best and most effectively for you in that front. The other one that probably catches most people out is that an int is an int in Python. It's because it's duck typed. It interprets the variable as whatever size variable it needs to. Whereas in a HDL language, people are used to having sized variables that wrap at particular sizes. They sign extend in a known way. Whereas if you don't take that into account with Python, it can be quite confusing, and you can try to send a number that's too big to fit into a sized variable, or you can ignore the sign by mistake. Those things can catch people out quite carefully if you're not careful. But to go back to your initial question of if is it a big risk, I don't think that's a language or a tooling issue. That's about process. And fortunately, verification teams and design teams have been quite good at this for a number of years now. It's not about one thing. You have to review, you have to cross-check. You'd have multiple different tools involved in the flow to make sure that you cover all your bases. We already do this with things like linting, variable synthesis, log checks, simulation checks. You really have to have a sort of a holistic approach as to how you sign off a product. Any one source of failure should be identifiable in that regard.
Yeah, okay. So I'm sure, as you're aware, we have been seeing falling first silicon success, probably because of the complexity of chips. But do you think there's anything in Python that will help stop that, essentially?
Uh,
Or
I,
will go
I, I
to
doubt.
the remedying that in any way?
No, I doubt directly due to Python. I think it's a consequence of how you spend your time. So, uh, in my opinion, I've very rarely seen. Maybe it's because of the companies I work for. I've very rarely seen a verification project stop a tape out. So the way most commercial projects work is when physical design have checked that the chip will physically work. At that point, you're ready to tape out. And unless your verification is in a state where you know that there are problems or you know that you haven't done enough work, it's very hard to stop that train from going from the station. Normally, with these projects, you know that there's going to be 2 months, 3 months in the fab. You've ordered boards. You've got software teams lined up for that chip to come back. You've got products that you know are going to go to NAM or to CES or to Mobile World Congress. You know you need to hit that demo point. So unless you know you have a problem in your verification, you're probably not stopping that train from going. So really, it's the quality of verification is one thing, but it's really about how much good quality verification you can do in the time you have, and therefore it's about productivity. And the more time you can spend debugging problems, the more time you can spend fixing those problems and spinning them is the benefit, as opposed to the amount of time you're spent typing macros to register variables for print statements.
Yeah. Okay, that makes a lot of sense. So Andy, when we had a chat beforehand, you let slip a little project you've been working on. Do you want to tell everybody that's listening about that project and what you've been
I sort of do. I'm also slightly terrified, but
working?
uh, I'll
Rip off
admit. So
the band-aid. Come on.
yeah. So I've in the background, I've been thinking about these challenges, and having used both Python and SystemVerilog pretty extensively over the last few years. Uh, One of the big problems I have seen with Python, like I just mentioned, is it's not just the language. Really, the things that would stop people from adopting Python uh, on a large scale way is that there is no VIP infrastructure. There is no common methodology to CocoaDB or Python that means that you could trust a vendor, whether it's EDA or open source, to develop you let's say an AMBER protocol or a PCIe protocol or DDR. This is where UVM really helped with SystemVerilog. It gave a structure that provided consistency in the ability to build VIP on top of the base class. So what I tried to do is take that principle and apply it to Python. Now, what I didn't want to do was take UVM and apply that to Python. There is already a Python UVM library. It's called PyUVM. You can go online, you can download it. It is perfectly good. It works well. But we've been using UVM for nearly 20 years now. We know there are limitations. We know there are efficiency challenges. So what I was hoping to do was take 20 years of learning and simplify this process. So I've taken what I've called AVL. I'm calling it the Apheleia Verification Library, which is almost certainly a name that's going to catch me out in the future. One, because it's quite hard to spell, and two, because people will just criticize me for it. But Apheleia was supposedly the goddess of simplicity. And the idea is to create a very simple library that gives us things that people expect to see in a verification environment. And what I mean by that is things like factories, which we use for overriding variables all the time, phases, so we have run phases and report phases, sequences, drivers, sequencers, and functional coverage. These kind of building blocks that you have for reusable, scalable verification environments that people are very familiar with and they expect to be there, which currently the Python framework doesn't do. I also tried, probably to my cost, to try and also address some of the things I mentioned previously. So Microsoft have developed the Z3 constrained random or the constraint library. It's actually really good. It provides you the same kind of constraints, implications, bidirectional constraint solver that you have in SystemVerilog. It's again open source, developed on the MIT license. You can do it. But adding that in so that people can construct classes which have multi-dependency constraints. So it gives you the randomization. And things like sized variables, again, it's a simple wrapper around a Python int to actually make it behave like an unsigned 8-bit variable or a signed 16-bit variable. And when you increment it or decrement it or OR it, it behaves as you would expect for a HDL variable. These kind of things to stop you making basic mistakes. Whilst I was doing it, again, probably more for a challenge than anything else, the other thing that's changed a lot in the last 20 years is the prevalence of floating point arithmetic, particularly with RISC-V has come out, and with machine learning, the usage of single precision or even half precision or quarter precision floating points is much, much more common. 20 years ago, not many people were developing floating point processors. I think with RISC-V, that's actually pretty common now for people to do. So what I've tried to do is create FP16, FP32, FP64 variables that you can treat as floating point numbers in Python and translate to digital floating point representation in Verilog.
How will this integrate into EDA? Is there any issues there? And how would you overcome them?
So it kind of depends on what kind of engagement you can get. So from a really sort of simplistic point of view, I've based it on CocoaDB for two reasons. The first one is I really like CocoaDB. It's a very good tool. It's solved a lot of problems and has a really active community already. But it already handles the simulator interaction. So it's already widely supported by Cadence, Synopsys, Mentor, Aldec. So the actual nuts and bolts of how the tool interacts with a simulator is done. So on top of that, how it interacts with EDA really is down to I imagine how it catches on. So there is nothing to stop. I'd be more than happy to engage with EDA on how we support this in case there's issues in that regard. But then what I'd really like to see is if we can somehow build a VIP community to expand upon this and provide. Right, I'm not saying this is going to be open sourced completely. If people develop useful tools on top of this library, They are fully free to go and commercialize that and do whatever they like from that point of view. Personally, I think the VIP licensing model could do with a bit of a refresh, particularly as chips have got bigger and you have to run more and more simulations. The idea of a seated VIP license where you can only run 1 or 2 simulations at a time seems a little bit outdated to me. That's the EDA company's problems, but I'm just hoping this could be a start point to start addressing some of these.
Yeah, okay. Um, you mentioned previously that obviously you want to be using SystemVerilog in certain situations still. Who is this targeted at? When should you be using this instead of UVM and SystemVerilog?
So this is probably hope over anything else. What I've tried to do is aimed at what I've tried to do is aim at everyone, which I know sounds like a real cop out for the answer. But for example, when I've been developing this, I have a very simple laptop. I bought it from PC World. It was £500. It's a Intel i5 processor. With Python and Verilator, which is another excellent open source simulator, you can develop HDL projects on a very basic shop bought laptop, which I would really hope is great for students, hobbyists, small FPGAs, or early stage companies. If people have got a burning innovation that they want to develop a piece of hardware for, but they don't have $100,000 to go and buy servers and EDA licenses and everything else. Now, I realize that there's EDA Playground, and some of those companies are being excellent in helping support early stage companies. But if you're just tinkering and you haven't quite got to that commitment point, hopefully taking this to add a sort of a commercial level verification environment on top of something like Verilator, which is openly available, could be a really good start point. But as I mentioned, the idea of adding methodology on top of the Coco 2B is to enable scale and for sort of commercial level EDA development. The ability to add reuse and the ability to construct complicated sequence-based environments is pretty essential if you're going to try and do anything at a commercial level. And hopefully this can scale to that degree. I've developed test benches and verification infrastructures for several companies over a dozen plus years now. Being entirely selfish, I can take this with me no matter where I go in the future. And I can donate it to companies I'm working with and everything else. It's almost a selfish act from that point of view. However, what I would really encourage people to do is look at how efficient they are being. Now, if you're doing a chip assembly and you're mostly picking up big bits of IP like PCIe, DDR, UCIe, USB, UVM is a great approach because you're going to probably buy that VIP from a serious vendor, and you will be able to put together your test bench much more quickly and effectively doing that way. If you're developing a lot of IP yourself and you want to have a high turnaround of tests, you're doing a lot of test development, all I'd like to encourage people is try it, see if it works for you. If you like it, hopefully it will be there for long enough that people can develop and continue with it. If you prefer SystemVerilog and you feel you're being super productive already, excellent, carry on with it. That's entirely up to you. But if nothing else, if you haven't tried a Python-based test bench, I strongly suggest you try it, see if you like it, and take it from there.
Yeah, okay. So how can engineers contribute? How do people find out more about the project? How can people get involved?
So it's at the moment it's currently unavailable. I will say that now. So
You've ruined the whole podcast.
Yeah.
Thank you.
So I'm presenting this at a Verification Futures. So Mike Bartley's event in the UK in I think it's the 1st of July. So before that goes live, it will be available in GitHub. People can download it and try it out themselves. I'll be very grateful. I've got a couple of people, a few ex-colleagues and friends who are currently beta testing it for me at the moment to make sure I don't embarrass myself the first day it goes onto the website. But at that point, it will be a GitHub project. Now, what I'm not expecting to do is it's not going to be open source in that I don't expect people to be contributing code willy-nilly. It will follow the kind of Verilator model or CocoaDB model where people are encouraged to contribute, file issues, have discussions. But if we want it to remain sane, small enough and compact enough to be useful, there's going to have to be a level of supervision. So at that point, I'd really encourage people to let me know how it's going and hopefully build up a community where people feel they can contribute. But I would really like to keep the base class small, simple, and possibly most importantly, readable. One of the things I've done when I've tried to write this is I'm not using any fancy Python constructs. I'm not using anything super complex. Partly because I always find if you have a problem, being able to read the code and understand what's going on is really important. So it's not obfuscated, it's not encrypted, it's completely there for people. But if we want to add things to it, whether it's VIP or just useful libraries, Python's great at adding libraries. So why not create a new one, tie it in, and try and expand it out that way? But we don't have to build everything into a base class for everyone. We can expand from that point.
Yeah. Okay. Well, Andy, I really appreciate you coming on. Obviously, it takes guts to go and start making something new. So really happy you came on. Really happy you announced on the podcast. And yeah, I'll see you next time.
Excellent. Yeah, no, thanks for having me on. It's been a pleasure, and see you soon.
Cheers, mate. Have a good one. So, thank you for watching, everybody. And Andy, thank you again for coming on the podcast. If you enjoyed that and if you thought it was insightful, please do like and subscribe on YouTube. And if you're on Spotify, please do follow and rate the podcast.